particle squared. So I need to know the velocities, and in order to know the velocities, I have to differentiate this radius, each radius vector with respect to time. Then the first term here will be the velocity of some point mass with respect to the reference frame O. And capital R dot will be the velocity of the second reference system with respect to the first reference system. And when I differentiate this radius vector, this one, I will find the velocity prime, the velocity of material point number k with respect to the second reference frame. Everything in the second reference frame will have this prime symbol. And all the velocities measured with respect to the first reference frame will have no additional primes. So that's the relationship between the velocities. The velocity of a particle in the first reference frame is related to the velocity of the same particle in the second reference frame, and the velocity of the second reference frame with respect to the first reference frame. By definition, kinetic energy of a system of particles is the sum over all particles mk vk squared over 2. So I will have to find the squares of velocities. That's what I will do now. In order to find the square of velocity, what is the square of velocity? V squared is scalar product of vector v by vector v. The scalar product of velocity vector by itself. So what is vector v? I know. I will take this expression and I will use it here. So I will have capital V plus vector vk prime and the same expression again, capital V plus vk prime. Simple algebraic calculations will give us this result. Capital V by capital V will give you capital V squared. That is the scalar product of vector V by itself. Plus small v prime times small v prime will be small v squared prime. Don't forget this. Don't forget that this is velocity with respect to the second reference frame. And plus 2 capital V times vk prime scalar product. When I write down this expression, I take into account simple fact that vector A, B scalar product equals B, A. In scalar product, you can change places, the order of multiplicants. So we have found the square of the velocity, which we need to calculate the kinetic energy. And I will continue this formula. Kinetic energy is the sum over all particles mk over 2. And instead of vk squared, I will use this expression. So that will give me capital V squared plus vk prime squared plus 2 capital V scalar product by Vk prime. So if I open these round brackets, I will obtain the following expression. Mk capital V squared over 2 plus the sum over all points Mk Vk prime squared over 2 plus 2 and 2 will cancel here, so it will be the sum over all k Mk capital V scalar product by Vk prime. In the first sum, V squared divided by 2 is constant. And I can factor this sum by this constant. I can take this constant out of the sum. So I will have V squared over 2. And what remains here? The sum of Mk. Plus the second sum, by definition, is the kinetic energy with respect to the second reference frame, where all the velocities Vk prime are measured with respect to the second reference frame. The same as the kinetic energy with respect to the first reference frame. The same expression, only Vk substituted by Vk prime. So this is, the second term is the kinetic energy with respect to the second reference frame. So I already have some relationship between the kinetic energy K measured in the first reference frame and the kinetic energy of the same system of particles measured in the second reference frame. Some relationship already is here. And what remains is this sum. Again, vector V is constant, and so I can take it out of the sum. I can factor the sum by vector V, and I will have V scalar product by such a vector which is the sum of many vectors Mk Vk vector prime. I continue these calculations. What is the sum of all the masses in the system? This is the total mass of the system. Total mass, by definition, total mass of the system. So what we have in the first term is capital M, total mass of the system, capital V squared, that is the velocity of the second reference frame with respect to the first reference frame, over 2. That's what we have in the first place here as the first term, plus kinetic energy with respect to the second reference frame. And what we have here, what is mass of a particle times its velocity? This is the momentum of a particle. And what is the sum of all momenta of all particles? This is the net momentum, or resultant momentum of all the system of particles. So this is the total momentum P. This is a vector, the total momentum. So what I have here is capital V scalar product by total momentum of the system of particles. There are many particles here. These particles may be a part of a solid body, or these particles may be a part of some liquid, or these particles may be planets in solar system, or maybe molecules of a gas, anything, any physical system consisting of any mass particles. So this physical system will have a total momentum which is the sum of all momenta of all particles involved in this system. And here is the scalar product of the velocity of the second reference frame, capital V, by the total momentum. So we have arrived at this interesting formula, which is a preliminary result in the Koenig's theorem. Koenig made another step, the next step in this derivation. He assumed that the second reference frame coincides with the center of mass of the system. So the question is, what if we measure the kinetic energy of the system of particles with respect to the center of mass of this system of particles? So the second frame O prime coincides with the center of mass. That is, I will put it so that this is a center of mass reference frame. In the center of mass, the velocity of in the center of mass, what is the momentum of the system of particles in the center of mass of these particles? We derived this formula that the momentum of the system of particles equals the total mass times the velocity of the center of mass. Total mass of the system of particles times the velocity of the center of mass is its total momentum. So if we are measuring this quantity in the system of reference coinciding with the center of mass, what will be the velocity of the center of mass in with respect to the center of mass? It will be 0. If you measure the velocity of this point from the point of view of this point, from the system of reference associated with this point, what will be the velocity of this point here? 0. So if we take the second reference frame coinciding with the center of mass of the system, then that momentum will be 0 by definition of the center of mass. So the second term here will be 0. And we obtain the final result in the Koenig's theorem, which is the kinetic energy in the first reference frame equals the kinetic energy in the second reference frame plus total mass of the system of particles, the velocity squared. And what is this velocity now? This is the velocity of the second reference frame with respect to the first reference frame. But we assumed that the second reference frame coincides with the center of mass. So now this is the velocity of the center of mass of the system of particles. That's the Koenig's theorem, final result, final formulation of the Koenig's theorem. It says that the kinetic energy of any system of particles equals the kinetic energy of the same system of particles in the reference frame associated with the center of mass of the system of particles, that is K prime, kinetic energy in the reference frame of the center of mass, plus the total mass of the system of particles, the velocity of the reference of the center of mass with respect to the first reference frame, the velocity of the center of mass squared over 2. So if you need to calculate the kinetic energy of some complicated body moving in some arbitrary way, you have first to calculate its kinetic energy in the center of mass reference frame. and then add mv squared over 2, where m is the total mass of the system of particles, as if it was all concentrated in the center of mass, which moves with velocity vc. That's simple and very important result, which allows one to calculate the kinetic energy in different situations. Let's consider an example. Suppose we have a wheel of mass m that rolls with velocity v, and all the mass is concentrated on the circumference. Here is all the mass, like a bicycle wheel. So the mass here is negligible, and all the mass is concentrated at radius r from the center. Such a bicycle wheel rolls by the road with velocity v. What is the kinetic energy of this object? Well, if you don't know the Koenig's theorem, how can you calculate the kinetic energy? You have to take each small mass delta am and take into account and calculate its velocity, and calculate its kinetic energy, and that will be repeated for each small portion of mass. And then you have to add all these kinetic energies, that is to integrate. That's too complicated. That's too awkward. Koenig's theorem allows one to calculate the kinetic energy in a very simple way. So, according to Koenig's theorem, kinetic energy of such a wheel equals what? First, yes, we can take it. The first is the total mass and the velocity of the center of mass, which is given here, v squared over 2. That is the kinetic energy of the wheel as if all the mass was concentrated in the center. It's not concentrated in the center, but the result is that it's proven in the Koenig's theorem that you imagine such an object, imaginary object, whose mass is concentrated totally in the center of mass, and the object moving with a given velocity, and then that will be its kinetic energy if all the mass was concentrated in the center of mass. But the mass is not concentrated in the center. The mass is concentrated along the circumference, and so the wheel is rolling, and I have to take into account this motion, and that is, I have to calculate the kinetic energy of this rotating wheel with respect to the center, with respect to the center of mass. What will be the kinetic energy of this wheel from the point of view of center of mass C? So we assume that we are in this reference frame associated with the center of the wheel. That is, we move in the same direction with the same velocity, so that the center of mass is at rest with respect to us. And in this reference frame, the wheel is just rotating, and all the mass of the wheel rotates at what velocity? Velocity v, certainly. Certainly the same velocity v. So that will be the kinetic energy in the system associated with the center of mass. That will again be mv squared over 2. So the result will be just mv squared. That is the kinetic energy of this wheel with respect to the ground, with respect to the reference frame associated with the ground. Any questions? So Koenig's theorem allows one to calculate kinetic energy of any complicated body moving in any arbitrary way. And Koenig's theorem makes it much more easier to calculate the kinetic energy. Because it involves non-trivial assumption that all the mass of the system of particles is concentrated in the center of mass. That's not true, actually. Actually, the mass of this wheel is not concentrated in this point. No, the mass is distributed over a complicated curve. But the Koenig's theorem asserts that the kinetic energy can be calculated in this way. One term, the kinetic energy is the sum of two terms. The first term is the kinetic energy of this body with respect to its center of mass. And the second term is such kinetic energy that is calculated in this simple way. We assume that all the mass is concentrated in the center of mass. And then we take the velocity of the center of mass with respect to the first reference frame, with respect to which we need to calculate the kinetic energy. That's the logic of this theorem. Also, I wanted to calculate as an example potential energy in some particular situation. We discussed the definition of potential energy last time, and we discussed it, and we concluded that a potential energy at any point in the field. What is the field? In physics, what is the field, by the way? Who knows? A field is such an object which is spread over space, and this object is characterized by many properties, but one property is very important from the very beginning. The single property is very important now, that such property that in each point of space some force will act on a probe body. If you take a probe body, a small mass or small charge, and put it here, some force will act on it. If you put this probe body in another place, another force will act on it. Another force, this is F1, F2. But in each point of space, there will be some force acting on a probe body. In each point of space, and the space may be infinite or may be finite, some area of space. We take some area of space. If there is a force acting on a probe body in each point of this area of space, then we say that there is a field. And a field is characterized, first of all, by forces exerted on the probe bodies. But also a field may be characterized by other things, by not only forces, but also energy density, for example, angular momentum density, etc., etc. So a field may have many complicated properties, but the first important property is the force property. The field exerts a force. And as physics was developing during centuries, people several times changed their understanding of fields. Several times. At first, people believed that forces are exerted just through the empty space. Newton believed in it, that gravitational force acts through empty space. Well, Newton, if you read his works, you will understand that he knew that that's not correct. There should be something which is acting on a body. An empty space, absolutely empty, if there is nothing at all, it cannot exert a force. If there is a force, there must be something in it. But Newton said that we don't know what is there. So if we don't know, we don't have to discuss it. No point in wasting time on discussing what we don't know now. Probably sometime later we will learn, we will discover what is there. But now, at this particular time, at this particular century, we know nothing about what is there. So we assume that there is an empty space. That was the first approach to fields. Second approach was such an understanding that there must be some medium in space. We don't see this medium, we don't feel it, we don't smell it, but there is something in space which exerts forces. So the field is something, material, probably something which was called an ether. Okay, that was the second understanding of fields. And then, in the 20th century, people understood that such an approach is too simplified. It doesn't fit into relativity, into special theory of relativity. It doesn't fit into quantum mechanics. So the concept of field was modified, and now people understand under field something more complicated. Something more complicated than merely an ether, like a mechanical medium. No, it's not a mechanical medium. It's, according to modern understanding, a field is a space area field with virtual particles, virtual quantum particles. That's a whole story. You will learn quantum physics later. Now we will just discuss how to take into account the force property of field. You remember there are many other properties, but we consider only one property, which is exertion of force, and how to calculate a potential energy in the field. So a 5 minutes interval. 5-minute interval. Okay, just a reminder, a simple example to remind you what is the potential energy and how to calculate it. If we are interested in potential energy at some point, potential energy is a function of r, radius vector, and this point has a radius vector with respect to some origin. We have to calculate the potential energy. By definition, we have to choose a point of zero potential energy somewhere in space. So we assume that here the potential energy is zero. At some chosen predefined point, we choose this level of zero potential energy by ourselves. According to considerations of convenience. It's convenient to believe that potential energy here is zero. Then, how can we calculate potential energy at any other point? We have to move a particle from the point of interest to the zero potential energy point and calculate work. And the potential energy will be equal to work done when the particle is moved from the first point to a zero potential energy point. How do we move this particle? It doesn't matter. We can choose any trajectory, this one or any other trajectory, any arbitrary path, any arbitrary curved path. Why is it possible? Because we have proven that in a potential field, the work does not depend on the path. whatever path you choose, the work will be the same. So we don't specify the path. We don't even have to draw any sketch of this path. We just say that the potential energy here is something with respect to the zero potential energy level. And this potential energy is defined as the work performed when a particle moves from the first point to the zero potential energy point. So an example will be gravitational field. Suppose here is some gravitational mass, and I will choose an axis to measure the distance from this mass, and I want to calculate the potential energy at some distance r from this mass, and the potential energy as a function of r, as a function of distance. First, in order to calculate the potential energy, I have to choose the 0 point, the zero potential energy point. It's convenient to assume that the potential energy is zero somewhere far away in space, where the gravitational field is zero. If gravitational field here is strong and here is somewhat weaker, and if we go farther and farther away, the gravitational field will vanish. So it's natural to choose the infinite point where there is no gravitational field at all. We know that gravitational field there is zero, so it's natural to choose an infinite point as the zero potential energy point. So in our particular case, when we calculate the potential energy in gravitational field, we understand that the zero potential energy will be at infinite distance. So the potential energy at distance r will be just the work produced by gravity forces if we move our probe particle from point r to infinity. How to calculate the work when we move a particle? We discussed it. We have to take an integral along the particle path of scalar product f dr, and the integral from distance r to infinity. In our case, the force is directed to the gravity mass, towards the gravity mass. This is the force of attraction described by the Newton's law of universal gravity. And delta dr, small displacement, is directed, it has opposite direction. As we move from point r to infinity, small displacements along the path will be positive, and the vector of force will have opposite direction. So the angle between dr and f will be 180 degrees, so the cosine of this angle will be -1. So when I go from vector form to scalar form, I must take it into account that a cosine here between these two vectors will be -1, and so the integral will be this one. The force, according to Newton's law of universal gravity, if mass m is here, is given by a well-known formula. The force is proportional to the probe mass, small m, and capital M, the center mass, the mass of the sun, for example, and the distance squared, the law of universal gravity, and dr. So this is a scalar form. I go from vector form to scalar form and immediately take into account this minus sign, because these two vectors f and dr are oppositely directed. So the scalar product will certainly be negative. And now I have to calculate this integral. What is constant here? Gamma is constant, small mass and capital mass are constant. So I can take them out of the integral sign, and the integral will be this one, dr over r squared. In order to take such integral, I have to recall that a differential of such function 1 over r equals minus 1 over r squared. It means that the integral of this function will be equal to minus 1 over r. So 1 minus and another minus from here, from this expression, will give me plus. Gamma small m capital M remains as a coefficient, and here I have 1 over r, and this expression should be taken in the limits of r and infinity. So it will give me gamma m capital M. First I take this in the infinity, in the upper limit, 1 divided by infinity minus the same expression at distance taken at distance r. What if we divide 1 by infinity, by infinitely large number? That will be 0, certainly. If you divide 1 by very large number, infinitely large number, you will obtain 0. So what will be here is gamma small m capital M and minus 1 over r. Minus 1 over r. So the final result for the gravity field will be minus gamma small m capital M divided by r. That's the potential energy in the gravity field. Potential energy of mass m, small m, in the gravity field created by large mass, capital M, and located at distance r from the central mass. The potential energy is negative. It means that if I draw this on a graph to show the potential energy as a function of distance r, then this formula gives you what? When distance r is very large, when it's infinite, this formula is 0, just as we wanted it to be, just as we assumed that the potential energy at infinite distance is 0. When you divide by infinity, you obtain 0. So at infinite distances, the potential energy is 0. But if you go to smaller distances, the potential energy will be non-zero. It will increase, the potential energy will increase in magnitude as r decreases. And as r goes to 0, this expression will give you infinitely large number, but always negative. So the graph of this function looks like this. That's the potential energy at distance r. That's the potential energy at distance r. So this negative quantity is a potential energy of mass m at distance r from the central mass. Such is the potential energy in the gravitational field. Also, you remember the formula that force is related to potential energy as minus delta potential energy. The vector of force can be calculated if you know the potential energy. Do we know the force? Yes, we know. It's a Newtonian law of universal gravity. But it would be good exercise to calculate, to use this formula. So this formula, when u is a function of only one variable, this formula will give you du by dr. We have to take a derivative with respect to r of potential energy function, and potential energy is minus gamma small m capital M divided by r. What if we take this derivative and take into account the two minus signs? What will be the force? Minus and minus will give you plus. The constant gamma small m capital M, and you have to take a derivative of 1 over r with respect to r. What is the force? Now we will calculate it using the well-known formula relating the force and the potential energy. What will be the force? What is the result of such a derivative? Such a derivative will be equal to minus 1 over r squared. So we obtain the result that the force, equals minus gamma m r squared. Why minus? Because the positive direction is here and the force will be directed here. That's why minus, right? The force is directed towards negative values of r, and the positive values of r are different. So we have calculated the force using this formula, and it's very useful in many situations. This formula is very useful. It will help you solve many problems. Next we consider what is there next? Scattering. Elastic scattering of particles. Suppose we have two particles, m1 moving at velocity v1, and another particle m2 which is at rest. What will happen when one particle strikes another particle and the collision is elastic? What does it mean, elastic? It means by definition that the mechanical energy is conserved. It's not spent, it's not lost. So if there is an elastic impact, then the particles will collide and then somehow move after collision in different directions. So this particle can move, for example, here after collision, and the first particle can move, for example, here after collision. So what will happen after collision? That's our purpose. That's the purpose of our consideration. We understand that the velocities after collision may be directed anywhere. We don't specify the direction of velocities after collision. We understand that these vectors may be arbitrary. So what happens in collision? In an elastic collision of two particles. In order to analyze this problem, in order to analyze this situation, it would be useful to consider this process in the reference frame related to the center of mass. Center of mass of these two particles moves with some velocity, which I will denote by Vc, velocity of the center of mass. How can this velocity be calculated? We have already considered this issue many times, or several times, and we know that the velocity of the center of mass is m1 v1 plus m2 v2 divided by total mass. In our particular situation, velocity v1 is given, so that is m1 v1, but the velocity of the second particle is 0 in our reference frame. The velocity of the second particle is 0. So there will be no second term in this formula, and what we obtain is just m1 v1 divided by m1 plus m2. That will be the velocity of the center of mass. And if I want to consider this problem in the reference frame attached to the center of mass, what should I do? How will all the velocities change? All the velocities will somehow change if I consider this problem from the center of mass. If I move together with the center of mass, then the velocity of each particle will be different. How to calculate it? From the velocity of any particle from the center of mass, as viewed from the center of mass, will be denoted by prime. That is another reference frame associated with the center of mass. So the velocity of the first particle, or any particle, will be found as the velocity in the laboratory reference frame, the first reference frame I call the laboratory reference frame, minus the velocity of the center of mass. So if I calculate it, I will find it as v1 minus velocity of the center of mass, that is m1 v1 divided by m1 plus m2. And this is, if I calculate it, if I take v1, if I factor this formula by v1, I will obtain m2 divided by m1 plus m2 v1. So that will be the new velocity of the first particle in the center of mass reference frame, as viewed from the center of mass. What will be the velocity of the second particle? If it was at rest in the laboratory system, in the laboratory reference frame, then as viewed from the center of mass reference frame, this velocity will be equal to minus v, minus the velocity of the second particle will be equal to minus the velocity of the center of mass, and the velocity of the center of mass is known. This is the velocity of the center of mass, m1 v1 minus m1 plus m2. That is the velocity of the center of mass with the minus sign. That will be the velocity of the second particle. What will be the momentum of the first particle and the second particle in the new reference frame attached to the center of mass? The momentum of the first particle will be what? Its mass m1 multiplied by its velocity v1 prime. By definition of momentum, we know the velocity v1 prime, and we use this expression here. So I obtain m1, m2 divided by m1 plus m2 times v1. And what will be the momentum of the second particle? The momentum of the second particle prime, as viewed from the center of mass system. That will be, by definition, the second mass, the mass of the second particle, times the velocity of the second particle, m2 v2 prime. v2 prime is here, and we can use this expression to obtain immediately the value for the momentum of the second particle. It will be equal to minus m1 m2 divided by m1 plus m2 v1. So what can you say about these two expressions? This is the momentum of the first particle, and this is the momentum of the second particle. You can easily derive from here that the momentum of the second particle, as viewed from the system of the center of mass equals minus the momentum of the first particle. They are equal in magnitude, these expressions are equal in magnitude and oppositely directed due to this minus sign. Is it surprising that in the center of mass reference frame, the momenta of two particles are equal and oppositely directed? It's not surprising. It's just the definition of the center of mass point. It's such a reference frame where total momentum is equal. The reference, one of the definitions of the center of mass, it's such point in space from the point of view of the reference frame attached to the center of mass, the total momentum of the system equals 0, so that P1 plus P2 equals 0 in the reference frame attached to the center of mass. And we have obtained this result, which confirms that our calculations are correct. So what happens in the center of mass reference frame? One particle, the first one, moves with this velocity, v1 prime. We have calculated it. So the first particle, m1, moves with velocity v1 prime. And the second particle moves with velocity v2 prime. We have also calculated it. And the second particle, m2, moves with the sign minus, which means that these two velocities are directed and now have different opposite directions. So that's what happens in the center of mass. That's this picture in the center of mass reference frame. And here's somewhere here is the center of mass point, which is at rest, because we are in the system of reference systems attached to the point of rest, to the center of mass. So this point is at rest with respect to us. We are now in this reference frame, and the two particles go towards each other to collide. And the collision will take place exactly at the center of mass point. And after collision, the particles will be somehow scattered. For example, M2 particle will go here, and M1 particle will go somewhere in different direction. In what direction will go the first particle and the second particle? We know, we have already discussed it, we have discussed a law of momentum conservation. When is momentum conserved? Momentum of the system of particles. When there are no external forces acting in it. And there are no external forces here. At least, even if there are some external forces, even if this happens in the gravity field of the Earth, in our Earth laboratory, there are gravity forces, external forces. But the collision takes such a small interval of time that during this small interval of time, the external forces will have no time to do anything visible. Their action will be negligible. During the collision, the action of, because the collision takes negligible time, very small interval of time, during this interval of time, small interval of time, the action of external forces will be very small, very negligible. So we can neglect the external forces if we are interested in the velocities and momenta of particles exactly after the collision. If we wait for a long time, we may discover that after the collision, this particle moves as a body thrown at some angle to the horizon. So the gravity forces will deflect the velocity of one particle, and it will move along some curved trajectory because external forces act on it. But this will happen later, and we are not interested in this phenomenon. We are interested only in what happens here exactly after the collision, during very small time interval after the collision. And if momentum is conserved, total momentum of the system is conserved, then what does it mean? Before the collision, what was the momentum? It was 0, because the momentum of one particle equals the momentum of another particle with minus sign. So before the collision, total momentum was 0. P1 prime plus P2 prime is 0, before the collision. If the momentum is conserved, then after the collision the same will be true. So after the collision, the two particles will go in opposite directions. So that will be the velocity of the second particle, of the first particle after the collision, and that will be the velocity of the second particle after the collision. We know that these velocities are oppositely directed for sure because of the law of conservation of momentum. And we know that the momentum of the first particle will be equal to the momentum of the second particle after the collision, because total momentum must be 0, because it was 0 before the collision. Okay, so the total momentum is 0. It means that the momentum of the first particle after the collision, how to denote it? The first particle after the collision, I will use such a tilde sign, after the collision, must be equal to the momentum of the second particle after the collision and opposite in sign, because the total momentum must remain 0, the sum P1 plus P2 after the collision. But what will be this momentum equal to? How to calculate? I don't know. How to calculate what will be? They are equal and they are oppositely directed, but what will be the magnitude of this vector? In order to calculate the magnitude, we have to use another conservation law, a law of conservation of energy, a law of conservation of kinetic energy or mechanical energy in this process. And I already told you that if the collision is elastic, then by definition of elastic collision, mechanical energy is conserved. So the mechanical energy must be the same after the collision as it was before the collision. So I have just to calculate the mechanical energy here before and after the collision, and mechanical energy of one particle, for example, first particle before the collision was mv1 squared over 2. And I will put it in this way. This is the mechanical energy, kinetic energy of the first particle. I will put it in this way. I will use the momentum of the first particle, m1v1. And I will multiply this formula, both numerator and denominator, by m1. So I will obtain this thing, p1 over 2m1. So I will prefer to express the kinetic energy not through the velocity, but rather through using the momentum. As momentum equals m1v1, and I put here momentum squared. Momentum squared will give me velocity squared, mass squared. But in the kinetic energy, I don't need mass squared, I need just mass. So I have to divide by mass. So I will obtain mass times velocity squared. So kinetic energy of any particle can be expressed in this way, using the momentum of this particle. So total kinetic energy of particles before the collision was p1 squared divided by 2m1 plus p2 squared divided by 2m2, which equals to now look here, p1 before the collision momentum of this particle was equal and oppositely directed to the momentum of the second particle. because we are in the center of mass reference frame. So these two momenta are equal before the collision as well as after the collision, because we are in the center of mass reference frame. So as they are equal, I will denote them simply by p squared. P is either p1 or p2 divided by 2, and here I will have m1 over m1 plus 1 over m2. So that's the total kinetic energy before the collision of two particles, where p is momentum of either the first particle or the second particle. In magnitude, these two momenta are equal, because we are in the system attached to the center of mass of two particles. What happens after the collision? After the collision, the kinetic energy will be the same, so I equate the kinetic energy after collision to the kinetic energy before the collision. This is the law of conservation of kinetic energy. So before the collision, kinetic energy was this one, and after the collision, kinetic energy will be something different. Again, I will use after the collision the notation of kinetic energy using the momentum. So that will be p tilde squared over 2, and the same expression, the same logic, 1 over m1 plus 1 over m2, because the momentum of first particle equals in magnitude the momentum of the second particle. Is equal to, these two momenta are equal. Oppositely directed, but when I find the p squared, this minus sign takes, this minus sign will not influence the result. P squared, p1 squared will be equal to p2 squared, and that will be equal to p tilde, the momentum of each particle after the collision. So if this expression is equal to this expression, from here we immediately obtain that p tilde equals p. That is, the momentum of any particle after the collision equals the momentum of the same particle after the collision. It's not the vector equality, it's a scalar equality. Only scalars take part in this, only scalars are involved in this formula. This is a scalar quantity because it's square. Vector squared, I remind you, is a scalar product of vector by itself, and the result will be just the magnitude of this vector squared. And here again the magnitude of this vector squared. So we can derive from this formula that the magnitude of momentum of any particle before the collision equals the magnitude of the same particle after the collision. What does it mean? Suppose that before the collision the velocity of the first, well, if momenta are equal, then the velocity is equal. The velocity of the first particle, the momenta of the first particle before the collision, and the momentum of the first particle after the collision. Again, I don't use vectors. I'm interested only in magnitudes, so I don't indicate vectors here. I have discovered that after the collision and before the collision, the momentum of the first particle is the same. So the velocity is the same by magnitude, not by direction. So if the magnitude of the velocity of the first particle was here, the vector, then after the collision, the vector will be different, but the magnitude will be the same after the collision. The magnitude will be the same, and the vector may be directed anywhere depending on how the two balls collided. The vector may be directed anywhere, but the magnitude of the vector will be the same. After the collision, the magnitude, the end of the velocity vector, will be found on the circumference of radius v1. It may be directed even here, v1. That is the magnitude of velocity. So in the center of mass, the collision of two particles turns out to be such that the velocity of the first particle will not change, will not be changed. The magnitude of velocity will not be changed. Only the direction will be changed. And the same is true for the second particle. If the second particle had the velocity like like this one, then the second particle. Then after the collision, its velocity will be found somewhere on the second circumference. So in the center of mass reference frame, the velocities of the particles remain in magnitude the same as they were before the collision. But the direction of velocity may be anything, any direction in space. So in the center of mass reference frame, that is the center of mass, the picture of collisions is this one. And what will happen in the laboratory reference frame? In order to return to the laboratory reference frame, I will have to add to each velocity the velocity of the center of mass. Because the center of mass in the laboratory reference frame was moving, here it is shown, the center of mass is moving with the VC velocity. So if I return to the laboratory reference frame, this point will be moving. And also each vector will be added to the velocity of the center of mass in order to return to the laboratory reference frame. What will happen then? So that will be the velocity of the center of mass in the laboratory reference frame, and that will be the possible directions of velocities of the first particle, and possible directions of velocities of the second particle will be resembled by a similar circle but of different radius. So the first particle was moving in some direction, and it may be scattered at some angle alpha, and we see that the maximum possible angle is limited. The maximum possible angle is such that sine alpha is this vector, the length of this vector divided by the length of this vector. The first vector is the magnitude of velocity v1, and the second vector is the magnitude of the velocity of the center of mass. Okay, let's finish this formula the next time. The next time I will start from here, and we need another 5 minutes to finish this topic.